We propose a crowd steering algorithm that uses an inverted pendulum model to efficiently plan short sequences of footsteps in space-time. Traditional steering algorithms use very simple models of how a character can steer, such as vector commands and a course collision radius, often disregarding the character's orientation and ability to sidestep. In contrast, our method has control over the exact steps used to steer, allowing a character to maneuver with spatial and temporal precision. By planning short sequences of steps that minimize energy cost, our characters exhibit natural human-like collision avoidance. To generate footsteps, we first choose a trajectory represented by a 2D approximation of a 3D inverted spherical pendulum model. Given the previous step and a chosen trajectory, we can compute an interval of biomechanically valid foot orientations for the next step, which is resolved as a simple post-process. A U-turn is a good example of the natural footsteps our method generates. The first step changes momentum towards the desired direction. However, because of footstep orientation constraints, the second step cannot be oriented towards the target. A third step completes the change in orientation, and the character resumes walking normally. The costs, constraints, and parameters considered in our approach can be easily adjusted to generate different locomotion styles, for example, an asymmetric limping gait. Steering with footsteps allows these two characters with different initial conditions to perform natural turns in narrow passages. A vector interface does not have enough control to reliably prevent motion synthesis from stepping over this ledge. We use dynamic collision bounds that allow characters to get naturally closer to each other while still properly avoiding collisions. An interesting application of our collision model is careful stepping. Note the nuanced side steps and turns chosen by this character to avoid the pits. Doorways are challenging because they simultaneously require spatial precision, temporal precision, and natural locomotion in order to look correct. Our characters cooperate at doorways with human-like fluidity and precision. This next doorway is so narrow that a single character can barely fit through. Vector-based steering algorithms would usually collide with the wall before eventually finding the door. Here, the red character finds that the least costly option is to stop and wait for others to pass. Also note the predictive steps chosen by other characters. Footsteps give our characters a large variety of subtle steering behaviors. This area shows characters stopping, sidestepping, and backstepping. Another view of this egress simulation shows the density of packing. Characters are comfortable packing close to each other without colliding. The performance cost of planning a short sequence of footsteps is amortized over the time it takes to execute those steps. Our footstep generation technique can support crowds of characters in real time on a single thread.